All right, another exciting day of circuits. I guess so. There should be some homework to turn in. Um, I will put up a 2 or 3 problem homework assignment for the inductor capacitor chapter 6 material, I think it is. But it'll all be very lightweight, something that you can probably dash off in a half an hour or something. Um, just so that you're feeling comfortable starting to see these things. Are there any specific questions? Because I got a lot of questions in the last 24 hours on doing some of these 7-in analysis things, and I have a couple of homework or problems out of the homework section that we'll take a look at. But if there are specific questions, I'll look at those first. Anything? Okay. Well, let's look at a couple of these problems out of the homework real quick, and that will get us started. So the first one is problem 548, and we're actually supposed to do this one as a Norton problem. So when we're doing a Norton analysis, what we're going to do is we're going to first solve. We'll remove the load, which is in this case the 3K resistor. The second thing is we'll solve for the short circuit current. We'll find the Thevenin resistance by doing the appropriate process of zeroing out the sources and then finding the equivalent resistance as seen from the terminals of the load. And then that'll give us a current source. It'll give us a voltage, or it'll give us a current source. It'll give us a parallel resistor, and we can then solve for the other component or the parameter that we want to look for in this case, which is the 3K resistor or the voltage across it. So first thing we need to do, pull out the 3K resistor, insert a short circuit, and solve for the short circuit current. So we'll still have the 3-volt source up here. We will still have the 2K resistor here, the 1K resistor here, 1 milliamp source here, 1K resistor here, and then we just have a short circuit over here. I think one tendency that students will sometimes have is to look at that and say, oh, well, there's a short circuit current, and so all of these other resistors just go away. Don't try to do anything like that. This does change the behavior of the circuit. The short circuit current in this figure is going to be different than the current that runs through the 3K resistor up here. But that doesn't mean, and that's also going to change the current that's running through all of the rest of the resistors. But in this case, nothing is particularly shorted out. So what can we do we need to solve for this current, so how might you do that? Yeah, a mesh analysis is probably a pretty good way to deal with this. So let's introduce 3 mesh currents, and let's do them conveniently so that, say, I3 will give us the short circuit current. I2 goes around the same direction as the 1 milliamp source, and I1 hangs out over here. So those are our 3 mesh currents. The 2 things to note off the bat are that I2 is 1 milliamp, and that whatever we solve for as I3 is going to be our short circuit current. So we write our mesh equations. The first one is -3 at the voltage source plus 2K times I1 minus I3 plus 1K I1 minus 1 milliamp equals 0. And then around the third loop, because we don't have to write one for here, but around the loop for I3, we've got 2K I3 minus I1 plus 1K I3 minus 1 milliamp equals 0. So we can solve those equations simultaneously. We've got two, right now we've got two equations with two unknowns, so let's see if we can simplify those a bit. We've got 3K I1 in the top equation. We've got negative 2K I3. We've got, this would be the 1K times 1 milliamp would give us a negative 1 volt. That would give us a total of negative 3 volt, or negative 4 volts. Put that on the other side, which gives us positive 4. So that's the first equation. The second equation, let's see, we've got negative 2K I1. We've got positive 3K I3. And then we would have a negative 1 volt from the 1K and the 1 milliamp. Pop that on the other side, so that should give us 1. So that is our series of our two equations that we need to solve for. Second, two equations, 3000 I1, negative 2000 I3 equals 4. Negative 2000 I1, positive 3000 I3 equals 1. And I get that I1 equals, looks like 2.8 milliamps, and I3 equals 2.2 milliamps. And as a reminder, I2 equals the 1 milliamp from the source that we had in there. So again, what we had determined before was that whatever we solve for I3 is going to give us our short circuit current. And so our short circuit current is this 2.2 milliamps. That's the important one. So when we start looking at our final Norton equivalent for this circuit, the first thing that we can say is that there's going to be some parallel resistance and a current source, and the current source is going to be 2.2 milliamps. We still need to find out what this Thevenin resistance is, though. So we kind of come back to our original circuit again. Well, let's come back to the original circuit up here. And so we'll redraw it. Wow, you can't see that at all. There we go. So now we'll redraw that circuit with the voltage source, or with the sources appropriately removed, so that, well, I think we can look at the top one to give me some room. So we we short circuit the voltage source, so there's just a short there. You got the 2K resistor here, the 1K resistor here. This is opened up. We got the 1K resistor here. And then we look at that all from the terminals of the load. So what is the Thevenin resistance looking in from those terminals? So we've got 2K, 1K, and 1K. So what do we have there? What's the first step to reducing that one?
2K and 1K in parallel.
Yeah, that'll be the first step. The 2K and the 1K here are in parallel, so 1 over 2,000 plus 1 over 1,000. That gives us, I guess that's 2/3 of a kilo ohm total. So if we get 2/3 of a kilo ohm and 1 kilo ohm. So the total then is going to be 5/3 of a kilo ohm as the Thevenin resistance. So we can plug that into our Thevenin equivalent, or our Norton equivalent that we had over here, which is 5/3 of a kilo ohm. And we can attach our load back on, which was a 3K resistor. And what we want to find is what is the voltage across that 3K resistor. given what we have, that's not a particularly fun thing to solve for. You know, I think in theory, if you were doing this and I just said, find this thing, find this circuit parameter V0, it might be easier to do this as a Thevenin equivalent, because instead of having to do a current division and then find out what the voltage is using Ohm's law, you could just do a voltage divider and get the answer. But in this case, what we need to do is we need to find out, let's call it current I0 that happens to be flowing through that 3K resistor. So current division, if we want to find out the current I0, we put the other resistor on the top. So we've got 5/3 of a kilo ohm over 3, make that look like a 3, plus 5/3 of a kilo ohm. And that fraction is multiplied by the 2.2 milliamps that are produced by the source. All right, so 5/3 divided by 3 plus 5/3 times 2.2 milliamps. Let's see if that makes a nice fraction. What my calculator says is that you get 11/14 of a milliamp, which is, you know, somewhere in the neighborhood of 0.79 milliamps, something like that. And then the voltage V0 will equal I0 times the 3K of resistance, which I guess gives you 33/14 volts, whatever kind of ridiculous number that is. But so does it make sense what we did? I've got one more that is dependent source only, because it seemed like there was a little bit of a question on that one in terms of how you're supposed to do that one on the homework. So this is, as you may recall, hopefully you recall at least a little, that when we have a circuit that contains only dependent sources, the Thevenin equivalent is just the Thevenin resistance. But whenever your circuit contains dependent sources, regardless of whether it's the only kind of source or if there's a mixture of sources, we can't calculate the Thevenin resistance in the same way. We can't just zero out all of the sources because that dramatically affects the makeup of the circuit and the way that it behaves. So what we have to do is we have to get both the current and the voltage across our terminals, and that will give us something to work with, I guess. So with the circuit that contains only dependent sources, we'll hook up a test source of some kind, whether that's a voltage source or whether it's a current source. Again, that's kind of up to you which one you'd want to do. When I look at this particular problem, I see this current source hanging out in the middle, and I don't like the idea of needing to deal with some sort of supermesh or loop analysis to solve for the current there. That sounds pretty nasty to me. So I would really rather do a nodal analysis on this one. And what would make that somewhat easier, I think, is, well, I guess it probably doesn't matter which one you hook up. If you hook up a trying to think. I don't really think that one is easier than the other. Which one do you guys want to see? Hook up a current source and solve for the voltage, or hook up a voltage source and solve for the current? Hook up a voltage source?
Yeah.
All right. So we're going to hook up a voltage source. We're going to hook up a 1 volt voltage source across the terminals A and B. And what we need to solve for, and it's important to get the polarity right here, is call that I0, I suppose. And our Thevenin resistance is going to be that 1 volt divided by the current that we solve for, I0. So I guess since we've got this as a, we hooked up the voltage source, we really only need to write one equation at V1, okay, right? Because we could write, we could write an equation at V2, but the only thing that we, regardless of whether there's 3 branches hooked out of it or 18 branches, it's hooked up directly between the reference node and a voltage source. So V2 in this case is 1 volt, and so we don't really need to write a node equation there. So we can just start writing the one equation at V1, which should make our life somewhat easier. The one thing that might be worth making 2 equations for is to, if we put a Vx over here, so that it's going to make things just a little bit more complicated, but it'll make dealing with the dependent source a little less nasty, I suppose. So let's put it in there just to make life, I suppose, a little easier. So we're going to write 2 equations for V1 and Vx. At Vx, there's just the 2 branches, and it's really pretty straightforward that you have Vx over 1k plus Vx minus V1 over 1k equals 0. So that's the first equation there. Then at V1, we write the equation V1 minus Vx over 1k minus Vx over 1k plus V1 minus 1 over 2k equals 0. So 2 equations, 2 unknowns. So we can try to simplify these equations and solve for the parameters that we need to. And realistically, what we need to solve for, and the way that we're going to attack this is that we will find out, call this one I2, call this one I1, and we'll recall that KCL in the first place says that I0 will equal I1 plus I2. So once we find out what the node voltages are at V1 and V2, then we can find out what the current I1 is, we'll find out what the current I2 is, and that'll tell us what I0 is. You could solve perhaps more directly for it if you were going to use mesh analysis instead. But again, because of that shared current source, that might not be a very fun way to do it, in my opinion. So let's try to solve this. Multiply both sides here by 1,000 to get rid of the denominators. We have Vx plus Vx minus V1 equals 0. And let's see, do this, multiply both sides by 2k to get rid of the denominators here. So we have 2v1 minus 2vx minus 2vx plus v1 minus 1 equals 0. So one of the things that we don't want to, it probably would not be a good idea to just put v1 on the other side. We'd really like to, I think, rather solve this for vx and get everything in terms of v1, solve more directly for v1, because that's the parameter that we're going to need going forward. So v1 equals, I guess, 2vx, but so we can divide both sides by 2, and anywhere that we see vx, we can replace it by v1 over 2. And to some extent, that should be like somewhat intuitive. I hope maybe just a little bit intuitive, because we had Vx was over one of the 2 1K resistors here. And the voltage V1 will be evenly distributed between these 2 1K resistors. That's what voltage division should tell us. So it shouldn't, I mean, this is just mathematically working out that Vx is half of V1. And to some extent, hopefully, there was at least some intuition that you could have done that in the first place. Just jumped right into that. So let's go ahead and stick that in everywhere we see it up here. So we've got 2v1 minus 2 times V1 over 2 minus 2 times V1 over 2 plus V1 minus 1 equals 0. So the 2's go away here, the 2's go away here, so we got 2V1 minus V1 minus V1 plus V1 minus 1 equals 1. So these three terms essentially cancel each other out. You get V1 equals 1. All right, so what does that mean? We've done all this work, and now we have a node voltage for V1. So now what we need to do is we need to go back and solve for each one of these currents, I1, I2, which will allow us then to use KCL to find I0, which is the whole point of all of this ridiculous analysis. So I'm going to move the circuit off the screen, but what we can say is that V1 minus V2 over 2K, that will give us I1, and V2 over 1K will give us I2. And that's consistent with the circuit as defined on the previous picture. And just as a reminder, V1 equals 1 volt, V2 also equals 1 volt. So we can kind of see what's going to happen here with I1. We're going to have 1 minus 1. So actually there's no current running in I1. All of the current in terms of this particular circuit, when you hook up a 1 volt test source to it, all of the current flows down through I2. And that happens to be exactly 1 milliamp. So I0 equals I1 plus I2. That's 0 plus 1 milliamp. And I think we can pretty easily see that that means that I0 equals 1 milliamp. What is the Thevenin resistance then? It's 1 volt divided by 1 milliamp, or 1 kilo ohm. So what that means is that practically speaking, if you have this circuit and you want to know what is the Thevenin resistance of that circuit, because I want to stick it in someplace and see what happens when I do that, and I want to analyze it ahead of time, well, I could stick a 1K resistor in there and it would give me the same behavior, as long as I didn't screw up any of my math. Does it make sense what we did? I think the most confusing part on this one is going to be the fact that is solving for that current at the end, because I don't think the nodal analysis is too tricky, and I think you did a good job on the exam dealing with the dependent sources, so I don't think that you have a problem with that either. The only question is, once you have those node voltages, how do you use those to solve for the current that you're looking for, that current I0? And it's kind of a roundabout way if you do it as a nodal analysis problem. But does that one make sense like the first one made sense?
It's easy when you do it.
So, are there any other questions on any of the homework problems similar to the homework?
You do 47.
47? So 5.47. So here's my poorly drawn rendition of the same circuit that is in the book for problem 547. And again, we're asked to do this as a Norton analysis problem. So what that means is that we're going to pull out that 2K resistor. We're going to solve for the short circuit current running through that. And then we are going to find the Thevenin resistance. So I'm looking at this problem and I'm not particularly thrilled to be doing it, to be honest, because the easiest way usually to solve for the short circuit current is going to be to do some kind of mesh analysis. And that pretty much means that there's going to have to be a super mesh or something going on in this particular problem. So what does our circuit look like that we're going to be working with? Because that's the one that's going to matter more than the original version of the circuit. We got the 2K resistor. We got the 2 milliamp source. We have the short circuit there. We have the 12 volt source and the 1K resistor. And we're solving for I short circuit, 2 mils, 1K, 12 volts, 2K, 1K. So that's the circuit that we're primarily going to be interested in. So in the hope that I'm going to try to do this without doing a super mesh, so that, because I really don't feel like doing one right now, and see if we can do it this way and get a reasonable answer. So let's say we're going to send I1 around this way, we'll send I2 around this way, and we'll send I3 all the way around the outside of the circuit. So our two kind of easy ones are going to be that where we see I2, that's going to be a negative 2 milliamps because it is opposing the flow of the current source. And our short circuit current isn't as easily directly solved for because it happens to be I1 minus I2 or I1 plus 2 milliamps. So we can write up all the rest of our mesh analysis equations going around. So I1, we've got negative 12 plus 2K I1. I don't like that. That worries me. Well, let's run with it and see how it works. I don't like this because in theory what this is telling me is that I can directly solve for I1, that I1 equals 6 milliamps when you put the 12 on the other side and divide by the 2K. And that's a little worrisome considering that I3 does flow through that loop too. It just doesn't flow through the 2K resistor. So I guess if this analysis is right, then I'm a little worried about it, to be honest. The short circuit current then would be the I1 is 6 milliamps plus 2 milliamps, should give us 8 mils. So that's what it would be with that one. Just to be safe, I want to do this one with the super mesh because this worries me a little bit. $1K, $2K, 2 mils, 12 volts, ISC. Okay. So we'll just define each of the loops going around in a clockwise manner. That's going to be I3. It's going to be I1. This is going to be I2. So our equations are going to change just a little bit. I short circuit is still going to be I1 minus I2. But instead, since we're doing the super mesh thing, we're going to have I3 minus I2 equals 2 milliamps. And then we'll start writing our loop equations. We'll introduce a voltage across the the 2 milliamp source, call it Vx with that polarity. So going around I1, we've got negative 12 plus 1, let's see, 2k I1 minus I3 equals 0. Going around the second loop, we get positive Vx plus 1k I3 equals 0. And then going around the top loop, we get 1k I3 minus Vx plus 2k I3 minus I1 equals 0. So it doesn't really matter, but we'll solve this one for Vx. So that's Vx equals negative 2k I1 plus 3k I3. So we can stick this in up here, and that gives us negative 2k I1 plus 4k I3 equals 0. And this one simplified is 2k I1 minus 2k I3 equals 12. And again, somewhat worryingly, there's, and it may just be the way that the circuit is put together, but we have these two equations, and we don't need this super mesh equation really, aside because I2 and I3 don't seem to share any components besides that source. So we're going to try to solve these simultaneously, see what the answer ends up being. Got 2,000, negative 2,000, 12, negative 2,000, 4,000, 0. And we get essentially the same kind of thing. We get that I1 equals, that's going to be 12 milliamps. I2 equals 6 milliamps. And we get that, the I1 minus I2 is our short circuit current, and that's 6 milliamps. So I guess the loop way worked out. It was just, yes, it was. So so I would be more confident in this analysis than in the first one, unless I messed up the math someplace. But
3 to 6 milliamps, right? And then you plug that into your equation. What isn't it 6 minus I2 equals 2, right?
well,
Or am I thinking about it wrong?
oh, you know what?
Because
These are not I1 and I2, are they? They're I1 and I3. And that would be a key problem. So we can't just do this yet because we don't have I2, we have I3. So to find out what I2 actually equals, I2 equals, well, the easiest way is going to be I3 plus 2, no, minus 2 milliamps, minus. So that's going to be 4, so 6 minus 2 equals 4. So we've got 12 minus 4 equals 8 milliamps. So it did work out okay the first time, and this is why I end up, why it takes me a bit of a long time to generate the solutions for the exams, because when I do stuff like on this first one where it's kind of like, oh, you can directly solve for I1, that's kind of scary. It's like, oh, that just doesn't seem right. But hey, it works out. So, and what all of that work does, we did it twice, and what all it really tells us is that when we start looking at our Norton equivalent, we've got an 8 milliamp source here. But we still need to find out what that Thevenin resistance is. So let's pull the circuit on so we can see at least a little bit. We start zeroing out the sources. So we short circuit the 12 volt source. We got the 2K resistor. We're looking at it from these terminals. We've got the 1K resistor that goes along the top here. This gets opened. And then we've got the 1K resistor here. And this, I will totally admit, is my weakest part of this entire class. I just have such a hard time when I start seeing these kinds of orientations of things as to what's doing what with what. But I think this is the same basic configuration that you end up with in, I guess it's problem 530, 525. Very similar to question 525, and what happens is these two 1K resistors are shorted out, and so all you get is the 2K resistor as your Thevenin resistance. Is it the exact same circuit?
Yeah, if they want you to do it.
Yeah.
So,
That's why.
well, okay.
And then
I got
was,
a different value for both of them.
so, are these more consistent with what should be the case?
I got
yours is right because you end up with 8 volts.
Okay.
In other things.
So if there's 2K here, and what was the load is another 2K resistor. So the 8 milliamps of current will evenly divide across those two. You'll have 4 milliamps running through each of them, and the voltage V0 will equal the 2K of resistance times the 4 milliamps of current, which gives you 8 volts, which apparently is the right answer.
5, but not 4.
Does it feel more comfortable?
Yeah, knowing that I got 100.
Okay. Does the process of doing the Norton analysis feel more comfortable? To be honest, I find Norton a lot harder to do. And it's just solving for the short circuit current. You end up getting weird things like we got in that first one, where I was just not comfortable with that I could directly solve for that. That's kind of scary, but. Sometimes it works for you. And Norton analysis, when you're doing the short circuit analysis, especially in the circuits that have the mixed dependent and independent sources, that's when really weird stuff starts to happen, and you have the independent sources going away, or the dependent sources going away and stuff. So, any other questions on homework problems or the Thevenin Norton stuff? Okay, well, let's start looking at the material from Chapter 6, which is technically the reason that differential equations is a prerequisite for this class. But the way that I learn this material requires no differential equations. The way that I'm going to teach the material requires no differential equations. But it is, I guess the downside is that it is a somewhat longer and more tedious way of doing it, because you end up drawing the circuit like 4 times. But because you look at the circuit, what does the circuit look like just before a switch is thrown? What does it look like just after the switch is thrown? And what does it look like well after the switch has been thrown? And then finally, what is the Thevenin resistance? And so you end up drawing, I think, 4 times in total, which is kind of long, but I think that in a lot of ways it's somewhat more useful as a analysis technique than the differential equation one is, especially because in theory, depending on how far we actually get, if we get to Laplace transforms, that would give us a problem-solving tool which is even better than the differential equation method. So So what are we talking about here? This is called first order and second order transient analysis. Essentially, again, we talked yesterday about inductors and capacitors in the high level, about how you combine them together when they're in parallel and in series, the relationships between voltage and current in these devices. And what we want to do now is we want to put them in circuits and try to analyze their behavior. Now, what you hopefully should recall is that when you have a circuit that contains an inductor and it has only DC sources, there's going to be a DC current running through that inductor, which means that the voltage is the derivative of the current. So there's going to be zero voltage, and it's essentially going to disappear from the circuit. With the capacitor, if you've got a DC voltage being applied to it, well, the voltage is constant, the derivative is zero, and so there's no current running through the capacitor, and it ends up, again, essentially removing itself from the circuit. But the time period in between when that DC source is applied to a circuit containing an inductor or capacitor is interesting, and it's interesting to quantify exactly what's happening there. When it comes to first order transient analysis, we're going to be solely looking at circuits that contain exactly one inductor or one capacitor. And if it contains the inductor, it'll be an LC circuit. If it contains a capacitor, it's going to be an RC circuit. That shouldn't be an LC circuit. It should be an RL circuit. It should be an RL circuit if it contains an inductor, or an RC circuit if it's a capacitor. When you put a resistor, an inductor, and a capacitor into a circuit, that makes it a second order transient analysis, because theoretically what we're doing is we're solving either a first order differential equation or a second order differential equation. And unfortunately, the more complicated and the more inductors and capacitors that you put into a circuit, the more complicated the differential equation gets. And all of the methods that we talk about break down extremely quickly when you start getting into more complicated circuits, and that's when Laplace transforms will make your life a lot better. So these are RLC circuits. We will look at simple parallel and simple series RLC circuits in a very cookbook manner. You look at them, you apply some theory, some formulas to them, you will give me answers, and that will be kind of the extent of it. So kind of what's the point? You've already been realistically exposed to this stuff in your daily life. So consider an old camera or even a new camera that you put in the batteries and you wait for the flash to get all charged up. You press the shutter button and the flash goes off, and then if you're listening, especially in some of the cheaper like disposable cameras, you can hear this high-pitched whine. And that's the sound of the capacitor being charged back up. And what you actually have in terms of like a circuit is you've got this battery, whatever it happens to be, some kind of resistance that's going on, and there's a switch connected between a capacitor and on the other, when you press the shutter button, the switch will move over to a different position where it fires, and this is the flash itself, which is more or less just a resistive element that happens to glow very brightly when current runs through it. So here's again, this is the battery, this is just some resistance, and here's the capacitor. And so what will happen is that current will run around this loop in the circuit until the capacitor is charged. And once it's fully charged, it'll become an open circuit. It'll stop drawing current from the battery, and it will sit there. And then once you press the shutter button, the switch will move over to this position. The battery will then be isolated from the rest of the circuit, and all of the voltage across the capacitor will now discharge relatively quickly across the flash. And so if you were to look at the voltage across the capacitor over time, what you would see is that eventually it would get all charged up to whatever the level of the voltage across the battery was. And then it would discharge very quickly and then come back up and then discharge. So each one of these is when a picture has occurred. You're taking a picture. And what is interesting to quantify are both the behaviors between this point and this point. How quickly does the capacitor discharge? And then simultaneously, how fast does it charge once you've taken a picture? How long will it be before you can take another picture? So this is essentially very practical kinds of stuff. And we can build up exactly what's going on. Did I leave that stuff in the note? Yeah. So if we look at the PowerPoint slide shows the same kind of stuff that I'll kind of show here, but so here's what is going on with that circuit. Again, this is the flash bulb itself. Here's the switch that will eventually be closed, and here's the capacitor. It's going to have some voltage across it. And if we write a KCL equation around this loop, so what is the voltage across the capacitor? A KCL equation. Is that right? A KCL around the loop. I'm not sure even where that comes from. But what you end up with, you've got a voltage across the capacitor with respect to time. That's the current that's running through the capacitor, and then the current that's running through. I am really not remembering where this comes from. I apologize. But that's a KCL around the loop. Let's see if I can remember where that comes from. Okay. This equation originates from being able to figure out what's going around. We can't just say, well, there's some voltage. To find out what the total current is that's running around in the loop, we've got the current for a capacitor is the voltage across the capacitor, the derivative of the voltage times the capacitance. That's the current through the, call it I sub C, it's the current through the capacitor. And then the current across the current through the resistor itself is the same voltage divided by the resistance, and that equals 0. So this gets us to there. And what you may recognize that as being is a first order differential equation with a solution of the form that the voltage across the capacitor with respect to time is some initial voltage V0 with e to the negative t over RC. And what that means is that based on the parameters of what the capacitance of the capacitor actually is, what the resistance of the flash actually is, and that there will be some drop in the voltage over time. And this will be, it'll start out at some voltage V0, and the slope of that line would be that negative e to the negative t over RC. And what we're going to do as we go forward is we're going to stop talking about RC specifically, and we're going to give that the Greek letter tau and call that the time constant. And that'll be something that will be important as we go forward. So that kind of gets us to, some of the motivation of what we're going to be trying to do here. And what the process, again, that we'll be more or less looking at are for these first order circuits will be that when you want to understand what the voltage or current anywhere in the circuit, regardless of whether it's across the storage element itself, with storage element being a generic name for an inductor or a capacitor, whether it's a voltage or current across one of those things or across one of the other resistors or whatever, it's always going to be defined by that first order differential equation. And there are the two chunks of that, the particular solution and the characteristic solution. I don't know if that stuff sounds familiar to you from differential equations or not, but the general form of our differential equation solution, regardless for any part of the circuit x of t, and that could be, this x of t could be, that's really skinny. Let's give me this one. This x of t, that might be I of t. It could be a current. It could be a voltage. It doesn't really matter, just as long as you're consistent in the way that you're solving for these two constants, k1 and k2. And again, tau is our time constant that we will quantify as either RC or L over R. So we'll look at that. But that's going to be the general form of all of the solutions for all of the first order differential equations that we'll see in this section at least. So again, like I said, you can solve these just using purely differential equation methods. And I suppose if you want to, you can. But I like this other method a lot better. And the step-by-step method that we're going to use goes as follows. We're going to start out with assuming that the form of the solution for this first order circuit is going to be that x of t equals k1 plus k2 e to the negative t over tau. And we're going to assume that the circuit, as drawn, has the switch in its original position and that the circuit has been at steady state, meaning that, that has some important, ramifications, that if the circuit is at steady state, that means all of the inductors have shorted out, all of the capacitors have opened up, and the circuit is going to be in a particular kind of configuration. And then what we're going to do is, depending on the type of storage element that happens to be in our circuit, we're either going to solve for the voltage across the capacitor, which is going to be a similar kind of solution to the open circuit voltage in Thevenin analysis, or we're going to solve for the current going through the inductor, which will be somewhat similar to, again, the short circuit current of a Norton analysis. And what we're going to call that is VC 0 minus or I sub L 0 minus, indicating that this has happened at some time, and a very infinitesimal time just before time equals 0. So then the switch is flipped at time equals 0, and we're going to solve for whatever the parameter is, whether it's a voltage or a current across the resistor or wherever else in the circuit. And we're going to call that I of 0 plus or V of 0 plus. meaning some infinitesimal time just after the switch has been thrown. Now what's going to become interesting or odd, I suppose, is that we're going to take the inductors and capacitors out of the circuit, and we're going to replace them with just normal independent sources. And if it's an inductor, we're going to replace it with a current source of the value I sub L 0 minus. So if we found that there was 3 milliamps of current running through the inductor at time 0 minus, well, we're going to stick a 3 milliamp current source into the circuit at time 0 plus. Similarly, if we solve for the voltage across the capacitor, we're going to replace the capacitor with an independent voltage source. And that will be the circuit that we'll use to actually solve for the original, 0 plus version of the parameter that we're looking for. So then we're going to draw the circuit again at steady state with the switch in its new position. And what that means practically is that it can be shown, and I think it discusses in the notes, that all it takes is five occurrences of the time constant, whatever that happens to be, because the time constant is a time. Interestingly enough, if you multiply resistance times the capacitance, you get seconds, and that seems odd to me, but that is the unit on the time constant. And when 5 time constants have elapsed, the circuit will be in its steady state condition. And so inductors short out again, the capacitors open up again, we solve for the final steady state version of that parameter. And then we find the Thevenin resistance from the terminals of the storage element, and we use that to solve for the Thevenin, or solve for the time constants itself, which gives us a final solution where the final steady state condition, x of infinity, becomes the value of K1, and the value of K2 is the difference between the initial condition and the steady state final condition. And again, that time constant goes as the fraction in the decaying exponential. So that's the process. I think we can probably work through at least one real quick and be happy with that. So let's see. So the slides give at least some amount of information about what it is that I'm actually doing, but most of the work will also be duplicated down on the paper, so you can take as many or as few notes as you want to. So the original version of the circuit looks like this. We have an independent voltage source, we have a resistor. Here's our storage element in this circuit. So all we have is the single capacitor. We've got a resistor. Here's where the switch lives. It is open at originally and will be closed at time equals 0. So when you start analyzing this circuit, essentially there's nothing on this little branch of the circuit initially. And it will close and simplify the circuit, and a big chunk will essentially, it'll be a very different circuit once the switch is closed. But then over on this side, we've got a 4K resistor and another voltage source. So this was 12 volts, 4K, 6K, 2K, 36 volts, and this is a 100 microfarad capacitor. And what we want to find is the current up here, the current running through the 6K resistor. That's what we want to find. So the first thing we're going to do is we're going to assume, well, this is a first order circuit. It's got exactly one capacitor in it, so we're going to assume that it's of that form, K1 plus K2 e to the negative t over tau. And so we're going to start our step-by-step process. So the first thing that we do is we look, we need to solve for the voltage across the capacitor at just the time just before the switch is closed, assuming that the circuit is at steady state before that occurs. So what does that look like? Well, we've got 36, we've got the voltage source. Here's the terminals of our capacitor, but the capacitor itself has been open circuited because it's been under DC conditions for long enough. We've got the 6K resistor here. The switch is open, so we can ignore that as well, more or less. Then we've got a 12 volt source. So what do we really have to analyze here? We have a single loop circuit. That's all that we really have to analyze in terms of the difficulty level of this circuit. Figuring out what exactly the voltage is across VC will be, a little tricky, but realistically, this is just a single loop circuit. So we can write a single KVL equation to find out, because if we go around this little loop, so we've got VC minus 36 plus V2K equals 0. So what that means is that the voltage across the capacitor is 36 minus whatever the voltage is across the 2K resistor, and that's just the KVL around here. So, but what we need to know is what is the voltage across the 2K resistor. To find that out, we need to know what the current is that's running around this loop, because that'll be 36 minus 2K times some current I. So we need to find out what that current actually is. So the KVL around the whole loop, we've got negative 36 plus 2K times I plus 6K times I plus 4K times I plus 12 equals 0. So that gives us a negative 24 on this side of the equation, positive 24 on the right-hand side. We've got 2K, that's 8K, that's 12K, so 12K times I equals 24, so I equals 2 milliamps. We can stick that up here. We got 2 milliamps of current, so 36 minus 4 gives us 32 volts. So again, that is the voltage across the capacitor just before the switch is thrown, or at time 0 minus. So the next step of the analysis then is to redraw the circuit after the switch is closed, replacing the capacitor with the voltage that we solved for. So what does that look like? At the circuit at time equals 0 plus, we've got the same 36 volt source here. We've got the same 2K resistor. This is where the capacitor was, and we're just going to replace it with the 32 volt source that we solved for. We've got 6K resistor. Now we have the switch is closed. We've got 4K resistor over here and 12 volt source. Yeah. $4K, $6K. And what we want to solve for is, this is I of t, and we want to solve for I of t in this case. And this is, specifically, this is I of 0 plus. Fortunately, with the way that the circuit is configured now, we can really kind of go to town with this and say, what is all the, do a nodal or mesh analysis or something. But realistically, if there's a current running around this loop, if we write that KVL equation around that loop, we get negative 32 equals 6K times I. I don't like that number. Oh, plus equals 0. And so I just equals 32 divided by 6k, which is the wonderful number of 16 over 3 milliamps. You'd think that as long as they were picking these numbers, they could pick them to be somewhat more intelligent instead of 16 thirds, but so whatever. So that is I of 0 plus. And we just kind of set that aside and say we will use that again because we need that for our constant K2. So now we draw the circuit at time equals infinity. Technically, it's really just draw the circuit at time greater than 5 time constants. For all intents and purposes, 5 tau is infinity because the circuit will behave the same from 5 tau until something changes the configuration of the circuit. So what does that circuit look like? Well, we've got the 36 volt source, the capacitor, whoops, we got the resistor, we got the capacitor open circuited again. So we'll draw on the terminal so you remember that it was there in the first place. Not like it matters, but it's there. We've got the 6K resistor. Here's where the switch has been closed. And then we got the 4K resistor and the 12 volt source. 6K, 2K, 36 volts. And again, we want to solve for I of t. And this is, and specifically, we're going to call this one I of infinity. So, unfortunately, these two loops of the circuit are more or less isolated from each other, or you could theoretically think of this whole right-hand side as being shorted out by the switch being closed. And so if we just write the 1 KVL equation around that loop, forget the subscript part, let's just call it I, get negative 36 plus 2k times I plus 6k times I equals 0. So 8k times I equals 36. And that means that I equals 36 over 8 milliamps. Or I guess 9/2 would be 4.5 milliamps if you want to think about that as a decimal. I've always liked decimals better than fractions myself, but. And so that, again, that's I of infinity. So we have 2 of the 3 things that we need. The last thing that we need to do is we need to find our Thevenin so that we can solve for the time constant tau. So that's the next thing that we need to find. So take a look at what the circuit looks like then. We've got the voltage source, that 36 volt source goes away. We've got the 2K resistor. I guess just so you remember, that's where, well, this is important. We need to remember that we're looking at the equivalent resistance from the terminals of the storage element. So we can't just kind of ignore the capacitor this time around. But then we've got the 6K resistor. The switch is closed here. For good measure, we'll stick in that 4K resistor, but that guy got shorted out anyways, so we can ignore him. We got the 6K resistor here, we've got the 2K resistor here, and this is kind of weird. What is the configuration? What is the relationship between the 2K and the 6K resistor? They're technically in parallel, and it almost doesn't look like that. But you have to realize that, again, we're looking at this from the terminals of the storage element. And so if you look at what are the two nodes at the end of each one of these resistors, you find that this node is this node is this node. Well, that's the end of the 6K resistor, and it's also the end of the 2K resistor. And then they obviously share that one. So the 2K and the 6K are in parallel. And that is one of the hardest things to kind of grasp about doing these things, these problems. So to find out the equivalent resistance, we combine them reciprocally. 1 over 2 plus 1 over 6. Flip that, we get 1.5 kiloohms. Therefore, the time constant tau equals the Thevenin resistance times the capacitance, or 1.5 kiloohms, times 100 microfarads. Micro is 10 to the negative 6th, so 1.5 E3 times 100 E negative 6 equals 0.15. And again, technically that is seconds. It's kind of interesting. So what that means, just as a side note, this circuit settles us, all of these circuits that exhibit this first order behavior settle down in 5 tau seconds. And so I guess that's 0.6 seconds, 0.75 seconds. So it takes 3/4 of a second for this circuit. Once you hit that switch, the circuit will settle into its new steady state condition in only 3/4 of a second. It's pretty quick. And it has everything to do with the Thevenin resistance, what is the overall resistance in the circuit, and the value of the storage elements. And you can, that'll be unique for every circuit. So we have tau, we have K1, or we have I of 0 plus, which was, let's see, I lost all of these. I of 0 plus is 16/3 of a milliamp. We have I of infinity, which is 4.5 milliamps, or 36/8, I guess 9/2, but whatever. And so K1, our constant K1 in our form, is just I of infinity itself. So that is just the 4.5 milliamps. K2 is I of 0 plus minus I of infinity. And cheating, fractionally, that works out to 5/6 of a milliamp. So we take all of these things. These are, I guess, yeah. And the final form of describing what happens for that current I of t over time is it's 4.5 plus 5/6 e to the negative t over 0.15. So it's a little long, to be honest, but in some ways I still like it better than trying to do it as a differential equation. So we will look tomorrow at how to do one of these things with an inductor in it. We'll also look at what happens when you start seeing dependent sources in these circuits, because as you might recall, finding the Thevenin resistance for a circuit with a dependent source means solving for both the open circuit voltage and the short circuit current. We'll do a quiz at the end of class, and I think what it will be is just to make sure you guys, and since we spent a lot of time reviewing the Thevenin analysis stuff, it'll probably be it'll be a Thevenin or Norton analysis problem, and it will be much easier than the one on the exam, and I can guarantee you that. So we'll do that during the last, say, 15 or 20 minutes of the class. Continue looking at this stuff. If you have any questions, please let me know. I will be in my office aside from a lunch with my family. Yeah, have a good one. We'll see you tomorrow.